I will be speaking about Destination Earth's on-demand extremes digital twin. So this is a project that is led by Meteo France, and there are several partners in this. I will go through this. And we do digital twin extremes together with ECMWF, where ECMWF will run the global modeling, and we'll run on-demand limited area modeling in configurable domains. The project is led by Elisabeth Girard and her colleagues Nadia Manon in Toulouse. The scientific coordinator is Roger Randré-Mampianina from Norway, and I'm the technical coordinator from DMI. So, just to give a context to this, I would like to go back to the year 1854 in the Black Sea. So what happened here was we had the Crimean War. I had presented this before and said that was the bad old days. Well, it's not maybe quite anymore, but many soldiers from many different countries were fighting and killing each other. And then one big event happened to show that they have a common enemy, and that was that it came a very strong storm. And many ships sank, and all the soldiers, they died. And what they realized was that if they had used modern technology, which at the time was telegraphs, they would have known the storm was coming because it was moving across Europe, and it was very predictable. Big storm coming, and then they all died. If they had shared this knowledge, they could actually have avoided this catastrophe of these people drowning due to the storm. So that's then the onset to starting the International Meteorological Organization, WMO, from 1873, 150 years ago. Buys-Ballot from the Netherlands was a main actor. He also made Buys-Ballot's law how winds are related to pressure gradients, as shown on the right. And then came Wilhelm Bjerknes, who set up equation systems to solve for the ocean and for the atmosphere how things will develop. So he was a student of Heinrich Hertz in the University of Leipzig first, and he could see there was these laws for electromagnetism that could describe all of electromagnetism, and he said, we can do the same for the atmosphere and ocean by combining Bernoulli's equations with the energy conservation equation. He saw in his lifetime the first computer simulation of a weather forecast on the ENIAC computer in 1950, done by von Neumann and Charny and his colleague Ragnar Fjørtoft from Oslo. So the physical modeling is important here when looking at extremes because we are looking also at events that never happened before. And then both human neural networks and artificial neural networks, they have a problem with these events that never happened before. So here's an overview of the contractors. So several of these are national weather centers from the World Meteorological Organization. So they are labeled in blue here. You also have experts in various fields. In the fields of computing, you have INRAE from France, who are hydrological modelers. You have REIVM from the Netherlands, who do air quality modeling. And, well, we span all across Europe, including some non-EU countries, Iceland and Norway. They can be in here because they support the Digital Twin or the Destination Earth initiative. So, what I'm very happy about, this is our first physical meeting we had in Norrköping in Sweden in December 22, is that all of these institutes are contributing with some of their top people, really qualified people, and they're really doing an effort. They're really happy about this project and taking it seriously. Our primary areas of focus is hydrology, air quality, and renewable energy. So renewable energy, as we heard before, is then getting to be really important. And in that aspect, we are all in the same boat, and we have the oncoming storm. So we need to be prepared. Schematically, our project looks like this. We can say you have the digital twin engine in this on the left-hand side, and then you have the impact systems on the right-hand side. And I'll be going through those impacts. Here's first some more background why we are going into this. We're also modeling for these domains at sub-kilometer resolution. It's the main point. So here's an example from 5 years ago, modeling Tassi Ilak, a village in Greenland. It's done by my colleague, Xiao Yang, who is one of the brains behind this project. Here we need the sub-kilometer resolution because you have very complex topography. and they get what's called the Pittorac winds. And since the last years, we've actually been able to model this successfully, which we couldn't before with the 2.5 kilometer model or with the 9 kilometer global model from ECMWF. And I'm also bringing up this slide to show we don't need to have observations at sub-kilometer level to be able to get good results from modeling at sub-kilometer level. Because we know the topography here, our input is 90-meter resolution, and we also have physiography data, for instance, from urban areas at very high resolution. We have currently 300-meter resolution. We are going down to 60 meters is our plan for the physiography data. And then if you want to model what happens inside a city, for instance, Paris, you really need this. We are running tests at even higher resolution. It's not a resolution we're actually aiming for, but this is done for the Alpine region between France and Italy by Météo France, Ludovic Auchip. He provided this plot of surface temperatures, and that's to test also the stability of the model, so really to put it to the most extreme test so that we are sure that it actually works. So it is a challenge to go down to these resolution also for physics, so we are jumping in the deep end of the water, and but it's a very nice challenge and it's very pertinent. We have made a list of test cases that we will look into. They are mapped here. There are various types of cases within the areas I mentioned, and also general severe weather and forest fires, which are low-hanging fruit when we are already running the NWP model, that comes rather more easily. So our hydrology work package is led by Ursula McKnight, together with Berit Arhammer and René Capel, all from Sweden. As I mentioned before, many other institutes also in here, and we have INRAE. And here are some of the cases that we are considering from many different countries that are in our consortium. So for air quality, we have this work package here, which is led by Markus Hirtl from Austria. Sorry, there's an error here. I should have changed the name of the institute. It's now called Geosphere instead of SAMK. They changed their name just this year. Mihail Sofiev from FMI and Gus Welters from RIVM. So here we are looking into two cases first. So we're doing our own in-house cases for testing in phase 1. So we have a cold inversion case, a winter case from the Carpathian region. So here you have data from Hungary, Slovakia, and Austria and Czechia in the top plot. And we have a summer case ozone event from Benelux. And finally, we have a work package here on renewable energy. Natalie Tevis leads this, and I'm actually co-lead. And here we are looking into wind events. So one primary thing which is shown in this example is the storm Eunice from February 2022. And here you see simulations of the wind power production in percent of maximum capacity, where you can see that on the left-hand side you have production in the Belgian region. We collaborate with the Belgian TSO, Gert Smit from the Royal Meteorological Institute in Belgium is in on this, where from 1 hour to the next the production completely stops here, and this is then simulated, and that actually also happened in the real world. It's a ramping event that when you have very strong winds you need to turn off the turbine, and then suddenly this electricity source disappears. And this is, of course, something we need to be able to simulate and understand. So, yeah, we also have solar energy data from the Danish TSO, and we have,